Today we're going to talk about the single source shortest path problem. So I need to define a few key things for our problem here. So we're going to let G be a weighted undirected connected graph with non-negative edge weights. So that just means that those numbers that we have on the edges that could represent, say, for example, the travel distance from one vertex to another. Just as an example, you can think of it just as costs too, or just as I'm going to call them, weights. That it has to be that they are 0 or greater. They can't be negative in the conception here. It's going to be an important detail for us. So I'm going to presume I'm given one of these types of graphs. So one other thing is that the graph is also simple. So that's just always a presumption I make. Otherwise, I would call it a multi-graph, just to be clear. So suppose I'm given a path. So that's just it's going to be given as, suppose I give you a path P. And this would just be a sequence of adjacent vertices. I'm going to give it as a set of edges in the order for which you would encounter them. So V0, V1, V1, V2. It's the same information. If I didn't have any edges, it means it didn't go anywhere, right? So I have V1. So it goes from V0, V1, V2, all the way up to the VK minus 1 to VK. So this is what my path would look like in terms of the edges. The length or total weight or cost of a path is the sum of the weights of edges in P, which I'll denote more formally like this. I'll call it the weight of that path, or the total cost, or the length. So I'll denote it like this, which formally it looks like this. The sum from I is equal to 0 to k, from where I take the weight of each one of the edges, and I'm just going to add them up. So we're going to be studying what we call the single source shortest path problem. And to do this, I'm going to need a little bit of terminology here. So let's get into this. So the first thing I need to make sure you are aware of is what is called the shortest ST path. So imagine I give you two vertices. It's going to be simply a path P. So it's some path P from S to T with minimum length. Right? That's what that means. So the first thing I really want to point out before we get into any examples is I really want to hammer in what a shortest ST path exactly is from a theoretical standpoint. So there's a very important property. In fact, there's going to be two properties that we would like to have at our disposal in regard to this problem. But before I define what this problem is, which the intuition is really simple, right? I have this graph. I would like to find the shortest ST path. So if I have some way of formalizing this, there's several ways you can do this. I'm going to formalize it a specific way later. I would like to have some property for these so-called shortest ST paths. So there's going to be two properties that we're going to use here. So there's going to be a couple useful properties. So a couple useful properties. So I'm getting really excited here. So the first one that we're going to discuss here is that if I give you a shortest ST path, I can actually decompose that shortest ST path into some set of subpaths, right? That are just like connected together like this. I could take those and so that I can end up with the shortest path. So each one of these little pieces of the shortest path are also shortest paths. So let me rephrase this a little bit more carefully. So what I'm saying is a subpath, so that's just a part of a path. A subpath of a shortest path is also a shortest path. So that's the first one. Now, you shouldn't let me get away with just saying this without anything in discussion. Now, I normally, when I teach this, I will either give you a proof for this or I give you the explanation for this. So the proof for this is rather nice and straightforward. So because we have the time, I'm going to prove it for you here today. So let's consider the following lemma. So this is going to be a key ingredient later for when we prove the correctness of an algorithm that solves the so-called single source shortest path problem. So here's a lemma. So suppose we are given shortest ST path. So suppose we're given a shortest ST path, P, and it has the same kind of form we just talked about, V0, V1, V1, V2, all the way up to VK minus 1, VK in G, as we've already defined earlier, where I'm going to assume that S, where S is equal to V0 and T is equal to VK. So now what we're going to do is we're going to consider a subpath. So let's consider a subpath. Consider a subpath. So consider a subpath P prime of P, where P prime looks like this. It's going to start at some vertex VI. And it's going to go all the way up to, actually, let me add another edge in here just to make it clear what we're talking about. It's going to be VI plus 1, VI plus 2. And it's going to go up to and include, as the last edge, VJ minus 1 VJ. And it's going to be the case that 0 is less or equal to I, is less or equal to J, is less or equal to K. So this is going to be somewhere along our shortest ST path. So I'm going to pluck off, I'm going to have I and J. They could maybe at the start, it may be towards the end. The point is it's somewhere in that path, P. It's one subpath in the larger path. So just to make this actually a little easier for us, I'm just going to give this a somewhat different name. Instead of calling it P prime, just to emphasize the point I'm getting at, I'm going to call it Pij, like this. I'm doing this deliberately, by the way. I just really want you to really understand that sometimes it's helpful for us to have special names for these variables. So subpath Pij is a shortest Vi Vj path of G. That's the lemma. So that's what we're going to prove here, is that Pij, this subpath, is in fact also a shortest path. It is a shortest VI-VJ path. So you might say, Dan, how are we going to go about this? So I want to kind of give you the game plan that I have in my head. And this is a nice technique that you can use in a lot of different contradiction proofs, specifically around those where a problem exhibits something called optimal substructure. That means that within a given optimal solution, you can find optimal solutions that you could decompose from it. So in this case, for example, I have a shortest path. I'm going to show you that, yeah, you can take a part of this path, one contiguous part of the path, that also has to be a shortest path. So I got to show you now how we can use that information to prove in the form of a contradiction proof how I can establish the truth of this, that it holds. So where do we usually start with a contradiction proof? I'm going to assume, so remember, this is the claim, the subpath Pij is a shortest Vi-Vj path, right? So to assume otherwise means what? It means that it's not, right? So we're going to assume that Pij is not a shortest Vi-Vj path of G, right? That's a good place to start to set up a contradiction proof. But what does that mean? What does it mean as a result? There has to be another Vi-Vj path, right? And it has to be shorter. That's what it means. Then there exists another Vi-Vj path, and I'm going to call this one P prime Ij. This is why I'm going to give this a nice name here. P prime Ij in G such that the length of P prime Ij is strictly less than the length of Pij. In plain language, this is just means that we have a shorter path. So let me draw you a fun picture of how we can use this to help us yield a contradiction. So what we're going to do is we're going to take advantage of a technique that very often is called cut and paste. So if I have a shorter path, what can I do with that information? Let me draw you just a picture just to give you a flavor for what we're talking about here. So remember, I have this path P. Starts at S. And it eventually reaches Vi. Keep in mind, Vi could be S. But the point is it's somewhere along this pathway. This is Vj. And we eventually get to T. Keep in mind, Vj could be T, for example. But this right here, all of this is Pij, right? That's what that is. However, in our setup here, we presume that there's another path. There's another path, Vi, Vj. So it goes from Vi to Vj. Now, I don't know exactly what's going on in here. It's just stuff, right? There could be some traversal through to get from Vi to Vj, some path. And this other path is going to be shorter. Do you see how I made it a little shorter? I just made it a little shorter. It could be any way shorter. This here is P prime Ij. Now, what I'm going to do is I'm going to use the fact that I have a shorter path from Vi to Vj to build a shorter ST path. Do you see how we can do it? Do you see how we can do this? let me just start us off, okay? So we already have, this VI and VJ here. So I was going to suggest that we construct a new ST path, P prime. So this is why I wanted P prime. By taking P and doing something to it. Do you see how I can make a shorter path from S to T, presuming that this is a shorter path than this one? Well, what can I do? I can just simply take this, put this here. You see I have this right here? I'm just going to put this path right there. And that's P prime. So P prime is just going to be the path from S to VI that I had up here. So I'm just going to take that part, put that there. I'm going to take this path from VJ to T. I'm just going to take that part. I'm just going to put that here. And then I'm just going to replace. So I'm just going to replace this guy with this. And I get P prime. So I'm just going to simply take P and replace, I'll say replacing subpath Pij with P prime Ij. But what does that mean if I measure the length of this path versus this path? Well, this one is strictly shorter than this one. So that means that the overall path that I just constructed has to be shorter, right? Then the length of P prime is strictly less than the length of P. But what does that mean? What does that mean? Can that happen? Is this possible? What is P? P is the shortest ST path. So can P prime exist? No, it can't. It can't. Which is not possible. Which is not possible as P is a shortest ST path. So that means that we simultaneously have that P, as a result of this, is a shortest ST path, but it also isn't at the same time. That is a contradiction. That's a contradiction. That concludes the proof. So that means that if I give you a shortest ST path, that means that I can take two arbitrary vertices in that path, and if I look at the subpath, that also has to be a shortest path. So this is a valuable detail for us, because that means that if I give you a shortest path from one vertex to another, to extend it to another vertex that is adjacent to one of the ends of this path is simply to, in a sense, extend it via some edge, or via an edge, to be a bit more precise. I'm just making up words here now. So that brings me to the second property here. So there is a tree, particularly if the graph is connected, it's a spanning tree. A tree of shortest paths from a source or start vertex. Start vertex S to every other vertex. To to every other vertex of G. So what we call this is a shortest path tree. So this is called a shortest path tree of or from S. So you might ask, Dan, what does this mean? Well, let me give you an example just so you can get an idea of what we're talking about here. There we go. We have all of them we have edge weights. I'm going to presume that this vertex here is S, and this other one over here is going to be T. This is an example of a shortest path tree of S. So notice that if I want the shortest ST path, notice it's just one of these paths in this tree, right? So notice I just go like that. And that's how I can get the path from S to T. So I could, in the same vein, I could start at T and work my way parent by parent, or what we call by its predecessor. So I could go for the predecessor of T to this vertex. The predecessor of this one is S. So I can work my way backwards or forwards depending on how I formalize the tree. So I called S a source vertex. And notice that I have a single source, S. I would like to find the shortest S other vertex path. That is an example of a path from the source to any other vertex in the graph. This is characterized by the shortest path tree of S or from S. So the single source shortest path problem is actually computing this tree. So you might ask, Dan, how do I know this exists? So I'm going to show you how we can build one of these trees. So the big thing I really want you to know about this tree is that every path from S to another vertex T in the tree is a shortest path. But the key thing here is that we have the source vertex. We're not computing all possible pairs of shortest paths. We just want all the shortest paths from this source vertex. And naturally, the former, what I just described to you, is what we call the all pairs shortest path problem. The latter is the single source shortest path problem. If we wanted to find the shortest ST path in a graph, so if I want to know how the shortest way to go from point A to point B, it's going to be in this tree. So, and you can see, based on some of the previous lessons we've had, how you can compute specifically one of those paths once you have this tree, okay? So what's the single source shortest path problem? Is compute a shortest path tree. Compute a shortest path tree from S. So S is called the source or start vertex to every other vertex. So that's the goal here. So I'm going to show you how you actually build one of these trees, okay? So one other detail I really wanted to point out to you, and you may not have caught on to this carefully, is that it doesn't matter for this tree if the path is simple or not. So if you were to just presume I'm trying to compute a simple path, it doesn't matter here. That distinction doesn't matter here. So notice that if you didn't have a simple path, you'd just be repeating edges or vertices, right? Which would simply mean that you're just wasting time, right? So I must stress that the shortest path tree, that this path that you get is a simple path. So that's just something I wanted to mention for you. So if you find yourself wanting to compute a shortest ST path that is simple, this is also capable of doing that. Pretty interesting stuff, right? And I must stress, remember, this is because of the setup we have for our problem, is that the graph has non-negative edge weights in it. So if that isn't true, we can't necessarily guarantee that the simple versus not distinction is the case. Furthermore, you can't necessarily guarantee that this tree exists. So what we're going to do now is we're going to see how we can actually construct one of these shortest path trees.